Hey guys, and welcome back to another A-Level Physics and Mechanics video. This time we're going to go through the graphs. So keep in mind, graphs are super important in A-Level Physics. They're going to come up again and again and again. But they're not always going to be the graphs I'm describing in this video. So again, in pretty much every single section, every single major topic, there is going to be a graph section because graphs come up all the time. However, the skills we talk about here are going to translate over to those other subjects anyway. So, for mechanics specifically, here are the kinds of graphs that you can expect to come across. So you're going to have the standard, you're going to have displacement time graphs, right? Displacement or distance, it doesn't really make a difference, so we can call it D or S, and it's going to be time. You also have your classic velocity or speed and time. And then last but definitely not least, we have the acceleration time graphs. Okay. And these are, again, super important. Acceleration and time. So why are these important? Well, what you're going to be asked to do is interpret what the different shapes of these graphs mean. You're going to be asked about gradients and also asked about areas under the curves. So what I'm going to do is I'm going to draw a few different graphs for each one, and then that way we can describe what it means. So the first kind of most standard case is probably something along the lines of this, a straight line. Okay, so what does this show you? Well, first of all, let's talk about what the gradient of this would be. So again, this is a key skill you're going to have to know for pretty much all of A-level physics because it comes up again and again. So whenever you're thinking about what the gradient of a graph gives you, and again, keep in mind they can give you any kind of graph, and you expect to be able to work out what it gives you. Okay, so that will make more sense as you go further into A-level physics, you'll see what I mean. But when you work out the gradient, what you do is you find the change in the y, and you find the change in the x, and you divide them, right? So in other words, if we were to look at the unit, so speed is most commonly in meters, and time will most likely be in seconds. Not always the case. You also have kilometers per hour, you also have miles per hour, you also have kilometers per day or something similar to that. You can have pretty much anything. But the idea here is you're going to have a distance unit over a time unit. Now what is distance over time? Well, it's always going to be velocity or speed. So we're going to call it velocity, but it could also be speed. So if this was a distance time graph, then you wouldn't have a negative section because distance can't be negative. It doesn't have a direction to it. So it'd just be this positive bit, so the speed's always going to be positive, right? If it has this negative part, then this is going to be displacement, which means the gradient will be velocity. So this is the kind of skill you can use, right? Just work out, okay, what units do I have, and what variables do those equal to? So again, if you think about it, if it's in meters and seconds, then our answer is going to be meters per second. But what does meters per second remind you of? It reminds you of speed / velocity. Okay, so those are the key things to remember. And then what about the area under the graph? Well, if we try and work out the area, again, we're going to do the same thing, right? To work out the area, and again, I'm not going to be specific, but overall you're going to times the x and y values, right? So if it's a rectangle, you just times them. If it's a triangle like this, you do half and then times them. But in terms of units, you're basically just going to be doing meters times by seconds, right? Now, if you think about it, do we have an equation that is distance times time? No. So basically, the area just doesn't equal nothing. It equals nothing. So when I say nothing, I don't mean it literally equals nothing. I mean that it equals nothing that's important. Okay? Now again, meters seconds is actually the units for moments, but in this case we're not talking about like moments, right? Or force or anything like that. So sorry, it can also be impulse and things like that. But again, this doesn't equal anything that we care about. Cool. So knowing these two facts about the gradient and the area, we're going to be given a bunch of different kind of situations. So in this case, the gradient, it might say something like, describe the motion of this object. Well, the gradient is a straight line, right? So the gradient is constant. So in this case, you're talking about something that is accelerating or has a constant speed. So it has constant velocity. Okay. which means it's not accelerating. Okay, so those are things you need to be able to describe. Likewise, we can have pretty much the inverse of this graph, and you can have it going. Okay, imagine that's going through the origin. Actually, you know what? Who cares about imagination, right? And again, we have the exact same axes. What about this? Well, this is going to be a constant negative velocity. Constant negative velocity. And again, it's not accelerating. Okay? But what about what happens here? Well, what happens when displacement equals 0? Well, it just means it's back where it started. And again, you can try and think of some situations in which this might occur, where you have a constant negative velocity or constant positive velocity. It's not dropping something, okay? Because if you're dropping something, it's going to be accelerating. Keep in mind, they can get a bit more complicated than this. So at the moment, it's going straight through the origin. But what if this displacement is 0 was actually a ball hitting a floor? Then you might have something like this, where it drops and then it starts up at the top again. Now, why does that make sense? Well, it wouldn't actually do it. It would go like this and then go back down again, right? Well, why does that make sense? Well, again, it's going to be bouncing off of the floor. Now, again, we haven't included the acceleration there, so imagine that in like a weird alternate universe. But then you can also have something like, and this is where things get a bit more interesting. You could have something like this. What's happening here? Well, again, imagine this is just velocity and time. Well, as you can see, the velocity, displacement and time. Well, as you can see here, the displacement is increasing faster and faster and faster. So the gradient is increasing. If the gradient is increasing, that means velocity is increasing, which means this object is accelerating positively. Whereas the exact inverse of this would be something along the lines of, it might go like very steep and then go very smooth. So it's beginning to decelerate. Okay. So those are the kinds of situations you can find yourself in, or any kind of, like, they can combine it, right? Like it could start off linear and then flatten off, which means the velocity is constant and then it slows down to a stop. Speaking of, what happens if you just had a flat line on a displacement time graph? That means it is stationary. The displacement's not changing with time, which means there's no velocity, which means they're not moving. Now again, let's do the same thing for velocity speed. So again, if we just considered something like this. Now again, we're going to look at the gradient. Well, again, we're going to take the y thing and divide it by the time. Well, this is velocity. In fact, specifically, it's the change in velocity over time, which is acceleration. Okay. Which is pretty useful, right? Acceleration's pretty good. So in this case here, the acceleration is constant and positive. Okay, so keep in mind you're going to have to use those words as well. So remember, all of these y-axes that we're going to be talking about here, they're all vectors, right? In terms of velocity, displacement, and acceleration, which means you need to say if it's positive or negative, because it has direction. Now what about the area? Well, in the area, we'll be doing velocity times time, right? Now, the other way to look at that is it's meters per second times seconds, which is meters, but there is a problem with saying this, right? Is you might say it's distance. It's actually displacement. Now, why do I say that? Well, if you look at the graph that I've drawn on the left, this velocity down here would be negative. So if I work the area out of this region, I will get a negative answer. You can't have a negative distance, but you can have a negative displacement. So bear that in mind, is that in a velocity time graph, if you're dealing with the positive area, which you mostly are, the examiner or the question will just say calculate the distance travelled, right? Because obviously it won't be negative, so the displacement is the distance. However, if it's below the x-axis, then the displacement and distance are technically different numbers. Displacement will be negative, distance will be positive still. So keep that in mind. It's just that in this top right region that we're dealing with, the displacement and distance are both the same. Okay, and likewise we can have the exact same situations that we had over here. So if we were to draw another graph, and I'll try and draw them a bit smaller so we have a bit more space, and again this is v against t, then this is going to be a constant deceleration. Something else to note is that deceleration is a bit of a wonky word. Technically it's still acceleration, it's just negative. So again, because we're used to cars, when cars slow down we say they're decelerating, when they're speeding up we say they're accelerating. In actuality, in both ways, in both cases, they are accelerating, right? It's just that in one case the acceleration is negative, the other case is positive, right? Deceleration is just negative acceleration, which is still acceleration. Okay, and then obviously you might have something that's like an exponential increase, right? So it might be like this. This is where the acceleration is constantly, well, maybe not constantly, but it's constantly increasing. Right, so it might not be constant, depending on, you'd have to differentiate this to work out if it is. And then likewise you'd have the same thing, which is where it's slowing down as well. Okay, so hopefully that makes sense for that one. And lastly, but certainly not least, we have the acceleration time graph. Actually one more graph I want to do with this one is if you have something like this, that looks like a cross instead of a, right? Something like this, it's obviously a constant velocity, which means there's no acceleration. Okay. This also means that when it comes to suvat, we can only use suvat in this case if it's a straight line. Okay, so please bear that in mind, and that should make sense because suvat is a constant acceleration equation, which means we can only do it when there's a constant acceleration. So if it's a straight line, or here if it's a straight line, right? It's just a is 0 in this bottom case. If it's across, obviously it's a flat line across here, then velocity is 0, so it's stationary. But in most other, like any other place, it's not stationary. Okay. In terms of working out the area, honestly, this can be really painful sometimes when it comes to A-level physics, because as you can see, we sometimes have big fat curves, right? You also sometimes have U-shapes, you also have N shapes and things like that. So how do you do it? Well, counting squares is the most popular example, but you can also use something similar to like a trapezium rule, which you may know from A-level maths, where you break it up into a bunch of trapeziums, find the areas of all of them, add them together. Painful, but necessary, unfortunately. If you're thinking about integration, you can only integrate if you know what the equation of the curve is. So 9 times out of 10 we don't know that. So with this one's a bit more interesting. What about the gradient of the acceleration time graph? Well, it's acceleration over time, specifically it's the change in acceleration over time, which doesn't equal anything we care about, right? But what you can say is it's also the rate of change of acceleration. So what I mean by nothing, again, is it's not a physical quantity that we define in A-level physics, so it's not something we necessarily care about. However, if they do ask you specifically for what it is, it's just the rate of change of acceleration. Yeah, and the area is actually a fairly interesting one. You probably already know what it is, right? It's just going to be acceleration times time, which is velocity. Okay, so it's kind of interesting. So if you have like a flat line like this, the area under it is the velocity. That makes sense, right? Because it's just a flat line, right? However, it also actually works if you have an increasing acceleration, right? The area under this curve here is also the velocity along this point, which seems weird because obviously since it's accelerating, the velocity is changing. However, keep in mind it would give you the average velocity. Okay? Because again, if something's accelerating continuously, right? So the acceleration is constantly increasing, then the average, it will be the average velocity instead, because the velocity is obviously constantly changing. You won't have it instantaneously, is what I'm getting at here. This is kind of a weird... This is kind of weird, however, what they like to do sometimes is they might... This is actually outside the scope of this particular spec point, but they sometimes give you circular motion. Now in circular motion, or things like resonance or oscillations, then it's common, or it is included that the acceleration would change over time. So it might be like a sinusoidal curve, things like that. But for the purposes of just standard mechanics, we're pretty much only dealing with constant acceleration or no acceleration. We don't normally deal with anything that looks like this. Okay, so that's quite a long explanation of kind of the different kind of graphs that we can be dealing with. And again, we may come on to different types of graphs later on. So for example, when we do momentum, there are graphs for momentum. This is specifically the ones for things like suvat. Okay. So again, I've got some questions from different exam boards. So a ball made from scrunched up paper is dropped from rest at time t equals 0. It reaches terminal velocity before it hits the ground. Which acceleration A against time? So first of all, the reason why they've included the terminal velocity, it means that air resistance is included. Okay? So, for example, someone might, in their ignorance, say, oh, it's B, because acceleration is constant, you're dropping it, it's gravity. Nope. Keep in mind, again, acceleration is a vector, which means you're talking about the overall acceleration. In reality, if I drop something, right, so again, let's say it's a piece of paper, right? That's my perfect piece of paper and we're dropping it. When it's not moving, acceleration is equal to 9.81 downwards. Then as it speeds up, you get this air resistance that begins to increase as velocity increases, which means the overall acceleration will decrease with time. So what we're looking for is an acceleration that starts at a value and dips. So it won't be this, acceleration wouldn't increase and then decrease. It would be more like this. Acceleration starts at a value, begins to decrease, and then it levels off, because eventually, as this kind of upwards acceleration is increasing, the velocity doesn't increase as quickly, which means this acceleration doesn't increase as quickly. So it actually tapers off towards the end. So the answer is actually going to be C. Because here, that's just G, but then as the ball of paper speeds up, the opposite acceleration is happening, which is why the gradient decreases. Okay? Because again, the more the velocity increases, the more this kind of counter acceleration increases, which means the velocity is not increasing as quickly, which means this doesn't increase as quickly. And then eventually it says it reaches terminal velocity. What's terminal velocity? It's when the upwards acceleration, so this value, equals gravity, which means you're no longer accelerating, which means you will go off to 0, which is exactly what C does. None of these others actually go off at 0, which might be the kind of key thing to eliminate. You know it's not constant because air resistance isn't included. Okay? You know it won't be constantly increasing, right? Because think about it, gravity would be constant. What would be speeding it up? What would be increasing the acceleration downwards? Nothing. If anything, it would be decreasing. So it's between one of these two. Well, it should end up at 0, so it's not this one. Hopefully that makes sense. So again, 1 mark questions, they are short questions, but they're by no means easy. They love to trick you. They love to backstab you. In this one, again, a lot of students just pick this one because they're reading, they're rushing, they're like, okay, it's falling, gravity constant, done, boom. Okay. This is one of our first kind of graph questions. So if you have a look, it looks like a combination of a few different pieces. So we have a metal ball released from rest. It falls vertically towards the ground. And figure 22 shows the variation with time t of the displacement s of the ball. So what's happening here? What is this, right? Well, it starts off at 1.25 meters above the ground, something like that. And it drops, and this is it speeding up because the gradient is getting bigger. It's getting more negative. So why is it getting negative? Well, they're taking upwards as positive by the looks of it. Okay. So, since this thing's dropping, it means the velocity is pointing downwards. and then it hits the ground and instantaneously stops because it's bouncing off. So it hits the ground, goes to 0 and then bounces off. And then here the velocity is now positive, and then it continues to decrease over time because obviously gravity is pulling it back down again. Resistance has a negligible effect on the motion of the ball. Perfect. The ball hits the ground at t equals 0.5 seconds, as we can see. During the collision, the ball is in contact with the ground for a time of 1.8 milliseconds. The mass of the ball is 56 grams. Again, this part of the question here, these last two lines, they're actually for a part that we're not going to include in this bit because it's to do with impulse, which is to do with momentum. So I've taken that out and I've put that into the other video. That comes later. So it just simply says, describe and explain the variation of the velocity of the ball from t equals 0.2 to t equals 0.7. No calculations are required. 4 marks. Okay, this is really important, the 4 mark bit, okay? So, here's what we need to do. Describe and explain means we need 2 describe points with 2 relevant explanations, right? So what I'm going to do here is I'm going to put a star for each describe point, and then we need to explain each point, okay? And there's a reason why I've done this, and this is a reason why exam technique is so important with A-level physics. It's unbelievable. And this is why I also say bullet point. In this question, it's very easy for someone to write all of the correct things, but only get 2 or 3 marks. Why? Because they've only described 2 things and they've only explained 1. Or they've explained like 3 or 4 things and described 1. Right? Or, and this is the tragic thing, someone gets 4 out of 4 but writes like 6 points, 8 points. So they've wasted 5-10 minutes on a question that only needs 4 marks worth of stuff. Bullet point your answers and you'll end up writing for 4 marks like 12 words. It's crazy, okay? And again, if you look at the mark scheme, it's all bullet pointed. They don't write in full paragraphs. Okay, so if we need 2 describe points, it says the variation in velocity. So we need to say how it changes. Well, if we look here, it's negative and then positive. So that's all we need to say. Okay? So, and it says explain it, right? So from 0.2 to 0.5 seconds, that's what I'm going to write here. So 0.2 seconds to 0.5 seconds, the velocity is decreasing, right? Is decreasing. Not just that, it's negative. 1 mark. Why? Well, because it's falling, right? Because the ball is accelerating downwards due to gravity. 2 marks. See how quickly that is? 2 marks meant to take me 2 minutes. 10-15 seconds? Bullet point, okay? Be really, really precise. Okay, and then it says the variation, right? So what I might say is at 0.5 seconds, what happens? Well, the velocity changes, right? And you can even get fancy, right? Instantaneously. Assuming you can spell it, which I'm hoping I can, changes from negative to positive. Also keep in mind, you can write a bit like a caveman. This is not like proper English, doesn't matter, right? At half a second, velocity instantaneously changes negative to positive. Done. That's it. Another mark. Now explain it. Well, it's because it hits the floor and then bounces up. This is because ball hits the floor and rebounds upwards. There you go. A lot of the time, what happens is, whenever I teach AS physics students, they write in full paragraphs and it looks very nice, and yeah. and then they end up getting like 2 marks in this question, even though what they're saying is 100% right. It's just that they don't have the right points. Okay, and that's kind of an unfortunate part about A-level physics, but you need the right points. Okay, you need to say the correct things at the correct times. So please keep that in mind. With A-level physics, again, by year 13, you're going to start bullet pointing everything. Okay, you're going to get 6 mark questions for like experiment. Bullet point everything. 6 bullet points, 6 marks, done. That's all you need to do. Part B, use an equation of motion to show that the speed of the ball is 4.9 meters per second just before it hits the ground. Okay, so all we need to do, S is 1.2, right? I remember that it's actually not 1.2, so let's work it out. So between 1 and 1.2, there's 1, 2, 3, 4, 5. So then we have 0.2 over 5. Actually, why am I even... get our calculators out, because A-level physics is just a calculator. So the way you work this out is... go away. You take the difference, so from 1.2 to 1, and then you divide it by the number of steps. So 1, 2, 3, 4, 5. So it goes up in 0.04. So this would be 1.24, right? So it's 1.24 meters. Also, just so you know, with your mock exams and your end of unit tests, a lot of the times in schools they use really low quality ink, or they like change the scale of stuff. So to me, this looks pretty damn clear, but in a lot of schools that I've kind of taught at, and like a lot of pupils that have given me their past papers and stuff, or their mock exams, these diagrams look really unclear. So if you have glasses, I would recommend just asking your teacher to make it bigger specifically for you, because again, these can come towards your mock grades, which is used for university. Anyways, the initial velocity is dropped from rest. Velocity is what I'm trying. So final velocity is what I'm trying to work out. Acceleration, of course, is just gravity because there's no air resistance, and time is, we do have the time. It's 0.5 seconds. So we can actually use any SUVAT equation we like. But I like to just use v squared equals u squared plus 2as because it's already rearranged for me. So v is just equal to square root 2, 9.81, 1.24. Whip out that calculator again. Square root 2 times 9.81, 0.24. 4.93, which is about... And again, technically this isn't like velocity, right? Because again, just you're going to have a good question here. Shouldn't it be negative? Your answer is yes, right? Because they've taken upwards as positive. So if I followed their convention and followed these values, I would get a negative answer. So the answer should technically be negative 4.93. The reason why it's positive is because it says the speed. Okay? Which means it doesn't have a direction, which is approximately 4.9 meters per second. And then lastly, possibly the most annoying thing that you have to do in A-level physics, draw a suitable tangent, and you have to do this to basically every damn graph that you ever get, which is annoying. If it helps, I've done this like 200 times and I still find it annoying, so yeah. So the rebound speed of the ball is 3.5. So people say, oh, how do I work out rebound speed? Think about it, right? This is the rebound here, so the rebound speed is just the gradient of this part. It's not like a new physical quantity. Now, drawing the actual thing, this is where things are going to get a bit interesting, because this doesn't work very well. So we need to find the steepness of basically this part here. So I could draw... That might be somewhat reasonable. Okay. So yeah. And I'm going to take it from 0.7. And the reason why I've done it from here is because the rebound speed would be that instantaneous part here, so I've drawn it right from the beginning. Now again, you do get a lot of leniency with this, so don't worry too much about it. Just make sure your line is straight. And if I read that off, like so again, I'm just drawing a dotted line. I know which line I'm following, which is why I'm allowed to go up and down. Well, I say it aloud, I'm not. But so 0.64, 0.68, 0.72. So the difference in this is 0.72 minus 0. So yeah, and this would be 0.7 minus 0.5, which is 0.2. Okay, so 0.72. And yeah, this is a 3-mark question. I've already done it, right? It's not too bad. So just whip out your ruler. And not just that, unfortunately in A-level physics you're going to be drawing a hell of a lot of tangents. Whoops. 18/5, so 3.6 meters per second, which is about 3.5. Not too shabby. At least I find, anyway. Once again, we have another multiple choice, so you might think, oh man, that seems kind of easy, but again, if we look at the graphs, in fact, I'm going to zoom out slightly so you can see all of them at once. Actually, that's better. So we have a velocity against time object, so we need to work out what the displacement time graph would look like. So again, we should remember that the gradient of a displacement time graph is equal to the velocity. So, let's have a think. In this first part here, the velocity is constantly increasing, which means in the first part, this gradient should be constantly increasing. And then, when it gets to this flat part, the velocity is constant, right? Which means we should have a constant gradient. So this part should look like a curve up, and then this part will be a flat part. So, which one shows that? It's part C. That would be my logic in doing this, okay? Just be very careful, right? So this is increasing, which means the gradient of the displacement should be increasing. The only one that actually shows that is one of these two. And, hang on a minute, is one of these two. And then when it goes straight again, so when I said constant gradient, I actually drew the wrong thing. I meant it's going to be like a flat line like that. Not flat, a straight line. So it's actually going to be D, not C. Brain fart there. But yeah, constant gradient would be a constant increase of displacement, okay? So again, very easy to make a mistake between those two. But again, you should be able to eliminate these two by the fact that the displacement isn't constantly increasing in either of those. So the gradient's not constantly increasing. Then all you need to do is it's a 50-50 choice from there. So that's my strategy in multiple choice questions, is eliminate the impossible, and it increases your odds by quite a bit. And then, yeah, look at which one actually matches it. So is it a constant increase, or is it flat? What's happening? But yeah, that's it for this video.